All right, I believe that's on. Yeah. All right, final exam. Oh, what I was going to say with regards to the homeworks. So I, because I was so delayed on those. So you'll see on Moodle. So I moved all the homework problems, all the homework solutions, all the homework assignments to one page there on Moodle. Just for your convenience, so you didn't have to think back. Oh yeah, what day was that we got all that stuff? So you have that kind of all there together. You're welcome to you're welcome to upload homework 5 and 6 as you like, but I'll say that I won't count. So I'm not gonna consider that as being mandatory as far as uploading that. Only because I think you can go through. So really, the valuable thing is try the problems the best you can with your book, with your friends, everything like that, and then um, just make sure that's right? And you'll go through that process of okay, I got the wrong answer. Let me go back and check, or I got the wrong answer. Let's see what he did for the first step, right? And then going through that process and making sure that you can do it, as independently as possible. That's really what matters, and that's the reason I do that. Um, the purpose of, well, you gotta turn in and show me what to do, really is just kind of as an extra incentive to encourage you to do that. But I think that for those of you that do use the homework as I've hoped that you've done, that having to go through that exact format, do it neatly enough to have it uploaded and be presentable, I think that's going to be an extra time commitment that I'm not going to ask of you. So don't bother uploading homework 5 and homework 6, but I would encourage you to go through them, do them as much as you've always done. As you know, that will really help you when it comes time for the exam. Okay. Let's talk about this exam. It's going to be Thursday. All right, now it's going to be Thursday. Man, it's going to be Thursday, and we're going to start at 7:45. We're going to meet in here, and it's going to go until. Some of y'all have classes. I mean, I'd even be fine meeting earlier. Well, I don't know. Remember how? Well, no, never mind. All right, what was I saying? Okay, so the exam. It's going to be just chapter 6 and 7, and I mean, really, there's not anything extra in chapter 8. But chapter 8 was where that's as soon as I get these homework stuff, I'm going to send that out. The chapter 8 is kind of a summary, of all the things that we've done. It kind of it reintroduces a lot of the tables that we've been using. It talks about time constant in the way that we've been talking about time constant, and some other things. And so really it's going to be 6 and 7. So chapter 6 is the electrical, but we're not doing, what's that thing called? It's like a triangle pointing to the right. That's the one. Stop before op amps. And then chapter 7, we're not going to be doing state variables. And there's some treatment of block diagrams, some in chapter 7, but I don't feel like we've covered that enough since the last exam to justify including that. So we'll say also no block diagrams. Okay. And this is cumulative in the way that to solve these, you're going to need to go back to the Laplace tables from chapter 2. You're going to need to think back to the solution methods for the spring damper mass stuff from chapter 3. But I'm not going to ask you questions that aren't related at all to this new stuff that we've been doing, okay? So cumulative, that's what I mean by that. So really it's just these homeworks. It's homework 5 and homework 6. It's the examples we've done in class, it's that sort of thing. So as long as you feel comfortable with that, then you'll be okay. I would encourage you. I guess if I could even post the blank one. So I posted the homeworks kind of all in one spot, and I hope that you've got access to your exam still. There's a lot, looking back at exam 1, there's a lot there that you'll recognize as things that we've done, the Laplace solutions, and same with exam 2. And I would encourage you as you have time to look at those. It may even be, depending on how well you did on those exams, it may be productive to go back and just take a blank sheet of paper and try to solve them. Again, just using your book or using whatever. I'll encourage you again, it's just a matter of, there's like a little speech I give, and it's this, as you think, because I'm sure this is your favorite class, but I'm pretty sure that it's not your only class, right? And so the next couple of days, I'm assuming, right, this is in the quarter, who's got another final exam in another class? Okay, so for some few of you, this is just kind of your only one. So if you're interested in the kind of advice I give with regards to studying, I'm going to show you two. Can you see that? Yeah, you can see that. Okay. Um, So these are really the 3 processes that go from here's the test question to here's the solution, okay? And so the first one, I'll just call it number 1. Okay, so this is time, and this is points, or importance, value, things like that, okay? So number 1 is drawing or graphical understanding of the problem. Number 2 is determining how to solve it. And then number 3 is the math to solve it. Okay. It takes a long time to write equations, to double check, to factor things, the quadratic formula. And so I would encourage you, where possible, to not do math over the next couple of days, right? Don't bother with, is my number right? Okay, you'd only do that if you're really not sure. But if you're studying with a couple of people, and you open up to a problem and you say, hey, could we solve this problem? it's just a matter of do number one and number two and stop there. Okay. And that's the advice I give when studying for exams is it's, the valuable thing is getting to that point where you can, where you know how to solve it, right? I mean, you think about uh, soccer players, they don't spend all their time running up and down the field in practice. It's very specific things, okay? Even though what they do most of is running up and down the field, okay? So you spend most of your time in the exam doing math. Don't practice the math. Okay? Practice that mental process of how to digest a word problem or a picture down into something that is that you can kind of visualize the process. And so I like to start off just kind of talking about that as far as what we'll see and kind of the thought process and how we'll divide things. All right. So we've got electrical. We've got fluid. And we've got thermal models. Okay. And there's kind of a mechanical analog that we do for a lot of these things. We've talked about that enough. I think we don't need to review that again this morning, right? There's an important question that you'll want to be able to spot really early on in the process, and that is this going to be a first order solution or a second order solution? Okay. A lot of times, second order solutions really require turning everything into the Laplace form, doing some arranging, and then going back to table 2.1.2, 2.1.1, and then trying to find it there and then turning it back into the time domain. Okay. First order isn't that way. Okay. If it's a first order equation, it's just a matter of, get a derivative, set it up in the equation, and then it's just b over a plus ce to the negative at. Okay. I don't think I stunned any of y'all by knowing that from memory. I hope that many of you do too, just for the amount of time that we've looked at that. As we've got electrical, fluid, and thermal. So with electrical, we're going to have, I'll just draw these here. We're going to have capacitors, we're going to have resistors, and then we're going to have inductors. Okay? So there's some different scenarios. If all three, it will be second order. All right. If there's only two, sometimes it will be second order and sometimes it won't be. Okay. And so the best way that we can kind of think about that is in the impedance kind of equivalent. Okay. And so I'll do that kind of here in parentheses. So the impedance here is an R. Here, this is a 1 over CS. And this inductor, it is LS. Okay. Oh, that's not important. That's my wife. Okay, and so you want to ask yourself, how many? I'm not sure how to phrase that question. So what's the difference between, or how many S's difference is it between LS and 1 over CS? I hope you can say it's a difference of S squared. Do you see that? So from having an S in the numerator to having an S in the denominator, you've got to either multiply or divide by an S squared to change that all the way. Can you see that? Okay, but if you're going from an R, which doesn't, if you want an R in the denominator, or so if you want an S in the denominator, divide it by 1S. If you want an S there in the numerator, multiply it by an S, okay? And so if it's a resistor and one other thing, it's going to be first order, okay? If you've got, and so you can just look at that with kind of the, I don't know what we call that, the order of S or something like, I didn't say the whole thing. The order of S, maybe, or some phrase similar to that. And then that would be first order. So I'm not sure exactly how to describe that. I'll say I'll say two types, right? Because you can have a whole bunch of resistors, whole bunch of capacitors. I'll say that are S to the 1 apart. Then that will be first order. Okay. I'm going to take a moment and kind of talk about those same things here with fluids and with these thermal systems. Okay, with fluids, in fluids we've got some, ooh, I got blue. Just because I'm sleepy doesn't mean I can't be artistic. We've got accumulators, okay? Accumulators work like capacitors, and we've got pipe. Okay, the pipe is going to have a resistance. The accumulators are going to have a capacitance. Okay, so if we think back here, okay, resistors and capacitors, that's always going to be a first order relationship. Okay, but I'm going to say it this way: each let's see, I'll say each independent equation will be first order. The important word here is independent, right? And what this kind of boils down to, let's see, how can I describe this? I think the following might be a good way to identify this. If the, and I'll need to think about this. I'm not sure it's going to be two. So I'm trying to describe what you'll recognize or what's unique about having two simultaneous equations. Okay? If you have, maybe I'll come back to that. I want to be a little bit careful. I'll say this: if there are multiple what's that word? When the equations are like related to each other, connected, or say again? Dependent. Yeah, I was thinking of a different word. We solve them simultaneously. Yeah, system. Okay, so multiple equations that must be solved simultaneously. Usually second order. It takes a pretty careful creation of a situation like that where it stays first order. That's typically going to be second order. We actually saw this in chapter 2 when we first, I think it was chapter 2, when we first started talking about the Laplace and the transfer functions. Well, even before transfer functions, where we would put it into the Laplace form, and then we could have kind of two dependent first order differential equations. We could combine them together, and we'd have now one second order equation that would represent kind of both together. And so that's the thing. So you will get first order and second order. Okay. That actually, I'll maybe put a note over here as well. That's the same situation here. So multiple linked first order equations can be second order. Okay. Yeah, so I'm trying to think of what you can spot. So certainly, if you've got two containers, or if you've got two capacitors and some flow, then you've got these two kind of components that are changing over time that are interrelated, okay? Which is different than one container. Well, but that's kind of two, but that ends up being first order. I'm thinking of the example that we did in class where you just have a constant volume coming in or constant mass flow coming in, and then a variable mass flow going out. Okay, you can solve for the height, you can solve for the outflow, and that doesn't get very complicated. Let's think about that, and I'm not sure we necessarily need to know this. You'll see some things, and if you can make the electrical equivalent, then that makes this pretty straightforward as well. I know there's some of you that don't like to do that, so let's talk briefly about the thermal, and then I want to mention we're going to talk about kind of the governing equations that we use, or the fundamental equations that we use kind of in that solving process. And I think from that you'll see, oh yeah, 3 equations, 3 unknowns. These are the equations that I use, and that sort of. All right, I'll just give myself a snap because I said the first half of it. Ow. And things similar to what I just mentioned as one example. Okay, thermal. I'm not sure exactly how to draw it. I'll draw it maybe like this. Um, Okay, in a way that can spring back. In a way that can spring back. Okay, so this is kind of key when we think about how this behaves. Okay, this is, a thermal mass. This is going to be like a capacitor. This is going to be like a spring. Okay, it's the idea of, I don't know how much of y'all do little electronics and that sort of thing. You can take a capacitor, put it in a circuit, charge up the capacitor, unhook it, and then go do something with it. Like a rechargeable battery. Okay, you can take a rechargeable battery, put it in a circuit, charge it up, then go do something with it. Okay, and this kind of adding thermal energy to use later, or taking away thermal energy, and you're going to intend on putting some back later. This is the type of thing where there's going to be storage or intentional depletion. You're right. There's going to be a mass related to that. I'll say that we'll have mass. And some specific heat. I can use the CP since we haven't done the ideal gases yet, or we're not going to do ideal gases. Okay. So this stores energy like a capacitor does. And spring. Okay. And then here, at the interfaces, there is resistance to heat transfer. Or I'll say to heat flow. Okay. There's resistance to heat flow. Let's see. There's resistance here to heat flow. Stores. Okay. Maybe those are some words that kind of help identify that. We said this is kind of mass related in here. So this is going to be either at this interface, this is either going to be convection or conduction. Okay. And that's going to have an R value. Like that green. And this is going to have a C value here. Maybe I'll make those green as well. Okay. If you feel comfortable with the electrical, that's a useful way. You can kind of put things back in that electrical analog and you can solve them there, but you don't necessarily need to. Okay. Let's talk about the equations. Okay. So for electrical, there's Ohm's law. I'll show you both forms. Okay, so this is the Laplace form of Ohm's law. Oh man, I'd remember how to spell it. It's here, HHOFF. Okay, so there's the Kirchhoff's voltage law, which is go in a loop. Sum of voltage changes 0. Then there's the current law, which says at any junction, sum of all I is going to be equal to 0. Right? Or all the current in is equals the current out, something like that. What was it I was saying? My next, if I have to escalate, I have a little tens machine that I hook up somewhere, some body part, right? And I'll zap myself with it. I guess that would be less. What's that word when other people see it? Yes, it'd be less conspicuous. So long as I can keep a straight face. The current in is the current out. Okay. Now there's Ohm's law, which is how we define this relationship between resistance, current, and voltage. But we also have two more. I don't know. I mean, I'm sure they're called something. I'll just repeat that. I'll repeat that. So for resistors, this is Ohm's law. Okay. For capacitors, it's the integral of the current. Whoops. I missed a 1 over c right here up front. We know we can manipulate this if we want voltage and everything, if we want current and everything. And for inductors, oh, actually, let me give you the other form. This is the Laplace form here. That's the Laplace form for the capacitors and the inductors. Okay. These are the equations. These are the equations that we use. So, I mean, unless you got some equation for your voltage input, you know, a step or an impulse or some fancier function, then this is it. Then this is it, right? We've got these voltage loops that will give us equations, and then we can handle this component by component, resistors, capacitors, and inductors, and from there we're going to get all of the equations that we need, okay? If it's a first order, it'd be 2 equations, 2 unknowns, right? You don't know the voltage, you don't know the current. Solve them either time domain or the Laplace domain, and then you will come up with some solution. Okay, there's really 2 places where the solutions are going to come from. Well, I'll say maybe 2.5 places. If I were to say put this back into an ordinary differential equation and you've got it in some Laplace form, then you need to use that table where you've got the relationship between the derivatives, right? The derivatives and the S's, fractions of S's. In general, to solve it, it's going to be look for forms. I'll say look for equation forms. Or look for term forms. Okay, I'll show you what I mean by that. Okay. This table 2.3.2, that's what I mean by an equation form, right? Case 1, case 2, case 3, case 4, or first order, and then here's the solution. Okay. When I say the term forms, it's going to be this. where we'll say, okay, well, I've got this S plus whatever, and I'm gonna convert that back into this. Okay. So this involves the Laplace. The one I just showed you does not. Did I pass it? Okay. So there's no Laplace in here. There's S's, which are kind of the characteristic equations. We're familiar with using that with the Laplace, but we can get our roots without that in many instances. So we don't necessarily need to use Laplace for this. Okay. There's this other table that is going to be useful. I didn't include it last time on the formula sheet. I maybe should have. You didn't need it, but there are some of you I noticed that didn't feel comfortable using the equation forms, and so we're trying to go back to this equation. I will include it this time because particularly with circuits and often with fluids, we're going to have some initial conditions, and which means with initial conditions, with yellow. So with initial conditions, you're going to need to include these terms here when you're doing your derivatives. And so there will likely be scenarios where you'll need to do this, and so I'll include that. Okay. So when I say equation forms and term forms, that's what I mean. Many of these you'll be able to solve using Laplace or not. Just depends on what you feel like doing. You'll notice in the solutions for homework 5 and what you'll see in the solutions for homework 6, in many instances I've solved it multiple ways just because you may prefer one way or the other, and so I show you both just so you can track or you can follow along in both. Okay. And so if you can think yourself to here as you're looking at a problem, as you're preparing, and certainly in the exam, but as you're preparing, if you can think yourself down to this point that say, you know, this is going to be a second order, I'm going to have a couple unknowns, I'm going to have 3 unknowns, I need to have some equations. If you can think through, say, oh yeah, I can see I can do Ohm's law right here across this resistor, or I can go around in this loop and I'll have this one big equation, Kirchhoff's voltage law, and it's going to have all these things in it. You know, if you can count up these equations in your head so that you can have all the terms that you need, then you can just stop there and say, I know how to do the solutions. I know how to do the solutions beyond that. Okay. Maybe I'll make one asterisk here, and I'll say some freedom. Okay. Meaning that you're never going to have 2 loops. I don't think. What I mean to say is you're never going to have 2 loops. I'll show it. I'm just going to scribble this and I'm going to erase it. So you don't need to, I just want to explain what I mean by this freedom thing, right? So if I've got a circuit here and here, or if I've got a circuit diagram that looks like something like this, and I've got, you know, components in here, wherever, that's actually 3 loops. I've got this loop, I've got this loop, and I've got this loop. Okay? You often don't need three equations meaning those three loops. And so you can just look and you can choose. And so you'll have some freedom there as you choose that. Don't get bogged down in choosing. Just do one, do another one, and you'll see that they're kind of all interrelated, and it'll work out for you. That's about as intricate as it's going to get with the electrical. And so 8:52. I think we'll have some time, maybe just at least to draw out some examples, and you can say, "Oh, here's how we'll solve it. Here's how we'll solve it that way." Okay. So we talked here about the laws. Let's do this quickly for the fluid and for the thermal, or the laws and the equations. Okay. Oh, did I star these? Well, I should probably star all of those. Okay, conservation of mass is an important one. Okay, there's some different ways that we see this, though, when we talk about the conservation of mass. Okay, I'll call, and so this would be, as you can guess, Q1 equals Q plus Q3. Okay. You may recognize that this looks very similar to Kirchhoff's current law, and it kind of is, in the sense that you're looking at junctions and saying, okay, everything going in needs to equal everything going out. Okay, so this case, I guess we'll call this no accumulation. Yes, sir. Sure. Thank you. Okay. Now, when we deal with accumulation, it's going to be a little bit trickier. Okay. Let's see. Yeah, I'll show you this first. We haven't talked much about pressure, but what I'll show you will help you understand kind of how we deal with the accumulation. Okay. So the pressure is going to be the integral of Q dt. I keep forgetting that. There's 1 over C. Yeah, I'll go in here plus M0 over C. Having this here, we hardly ever use that, only because often the next step is we differentiate this equation, and so this term just goes away because it's a constant. Okay, and then this shows up in our initial conditions. Once we have the equations, we're solving for all of our C coefficients, and that's where we'll see these. Uh, you know, let me. I'll just make a note right here. This term often disappears. You'll see your initial conditions when finding the coefficients. Okay, so often you can solve this without that equation even, and then you'll be fine. Okay. So I say here there's no accumulation, okay? And so it's simply, okay, I've got some coming in all these different directions, dividing up, it's got to be equal. But with accumulation, I'll show you this equation, you're gonna say, well, of course, that's kind of dumb.
So that pressure equation is still for no accumulation?
No, this is with accumulation. So what we have here is a situation, I'll just draw it like this. Where this is my Q1 and this is my Q2. Sometimes I do my hats, sometimes not. Right, so yeah, sure, you'd say it's going out, it's going out. Okay, it's going out of the accumulator and into a pipe, or vice versa. This is really important interface though, because this is where we do a lot of our relations. Okay, because we've got the accumulators here. And you know what, maybe I should put that down with the no. What I'm about to show you really this is in scenarios where there is generally accumulation, because that's where this becomes a dynamic system. And so I'm not going to put up there with the no accumulation, but it'll be the pressure drop okay. So in pipes, and then accumulators. How about that? Okay, and so we solve these. Again, we're going to have a certain number of unknowns. Sometimes it's a height, sometimes it's a flow rate, sometimes it's pressure. I guess pressure and height are kind of related. And we're looking for equations that we can solve simultaneously using the Laplace method. Okay. Now, I've shown you this form, and I've shown you this form. Okay. Did I do that backwards?
I think the flow rate should be the pressure divided by resistance.
Yes. Thank you. Yeah, I was just thinking to put this back into the kind of Ohm's law analog. I call it that. You okay with this version? This form of it? Okay. Glad I got an eraser. You know, 60 years ago, if professors never made mistakes, you wouldn't need an eraser by the chalkboard. You just have lots of chalkboards. Well, I guess that's not true. Okay. So these are the standard forms. Again, if it gets, you can solve it without putting this into the Laplace. If you want to put these into the Laplace, there's a few different ways that you can do that. Okay. You can come and say, you know, we've got a constant, we've got a integral. Let me go back and look at the tables and see how that all plays together. Easier, let's see, maybe in a different color, in the Laplace. If I put a big Q, that's going to be kind of weird. I will, though. And then here, I'll put it kind of over here. Close. Okay. I'm tempted to just leave these as little cues. Well, I'll keep the hat on it. Maybe you'll be able to understand. I don't mean that to be charge. This is not related to the charge. This is related more to the current. All right, V equals IR, P equals QR. So the Q is more like the current. Okay. Don't worry about calculating R. This will be either given or not. Okay. We went through kind of some derivations where we talked about the Hagen-Poiseuille formula and how that turns into a flow resistance, you know, orifices versus pipes, and there's different ways that you can calculate that. Don't worry about that. that you'll either have an R, I'll say treat it linearly and this is what it is, or not. Okay. So we're going to assume that R, if you're going to have to solve this, you can assume that the R is going to be linear. I'm not going to ask you to do any linearization.
Will you denote if the flow is laminar or turbulent?
Nope. I will say because turbulent uses
A p value?
yes. Now there's a way to do that. If you think this is going to confuse you, then fluid resistance. And don't look at this. Okay, so this is what we've been talking about if it's laminar. If it's turbulent, yes, we've got this, but there's also kind of a modification that you can do by using kind of this reference flow where it is manageable, but you've got to have B, you've got to have this reference. We're not going to be doing anything like that. So I'll say that you can ignore turbulent or laminar. Okay. This is a very, very useful thing. When you've got a situation, you're asking yourself, okay, what's the Reynolds number? Is this laminar? Is this turbulent? I really do need to calculate these. So keep your textbook in case you need to do this, like for your job. But for this exam, I'm not going to ask you to do that. Where we go through the Reynolds number and do all those calculations here. So I'll say this is a linear resistance. And if you hear linear resistance, that means it behaves like it's laminar. Okay. And so that'll be laminar or turbulent or orifices. I could say, and that's one of the runs. This behaves in a laminar way. It just makes it easier to solve.
Well, the flow rate equation is different between like if it's an orifice or if it's laminar. Like the mass flow rate has a square root of pressure over resistance.
Yes, which is nonlinear. Okay, that's nonlinear, and so we're not able to solve it using there's no forms for that. Okay, and so we're not going to be doing any of those nonlinear equations. So typically when we think about pressure is height, and height is this variable that we're looking for. Okay, we can handle a height times any coefficient. We can handle the first derivative, the second derivative of height, but height squared now makes that nonlinear. Okay, and so we're not, or height to the 1/2. Okay, so we're not doing that. Okay. For the exam, I would feel like you'd be able to proceed if you needed to do this. But for the exam, I'm saying either it'll be linear and solve it as if it's laminar for orifices, for pipes, laminar or turbulent or not. Okay. What I've shown you is we've got these equations, these flow equations here and here. Okay. And so a lot of the attention that you'll want to be giving is going to be at interfaces, or I'll say at, so I'll call this kind of an interface, or, I'll call that a junction, maybe draw this red. So this is kind of a key point right there. Whatever you see pipes and accumulators coming together, this is going to be key. All right. What we have here this is not a constant relationship. Okay, this is the pressure and you got this function of the flow rate. There's one other there's one other pressure equation that we often use, and that was that the pressure is rho g h. Okay, if the pressure is rho g h, then P dot is going to be rho g h dot. Okay, and so we can use this for accumulators, and this is the pressure variation with depth. Due to gravity. Okay. And so often while you're drawing these equations, or where you're trying to come up with these relationships, if you're on this side, you've got a pressure, and you can calculate what that is. Often if you got an accumulator that's open, it's just rho gh. That's the pressure, and you can also find the change in pressure. There's one example in the homeworks that's got an accumulator with a spring. All it does is, instead of rho g times h, it's rho g plus something else, all times h, or all times h dot, and so it's not complicated. If you think about the spring, right? In the one problem for the homeworks is I've oriented it such that it's going to be straightforward. That the h you would use for the pressure here, the rho gx, is the same h that you would use. I'll just do this. Here, I'll do it in white. How about that? Just kidding. White's not a very good color. So this is more of kind of the homework thing for the spring. I don't know if you got there yet. That'd be the force is KH. And so the pressure is force over area, like that. And so in that homework, that I've set the problem up so that H is X, or X is H, kind of. That's the same number there. Let me see. Okay. Oh. Yeah, I need to get a newspaper. That reminds me. Where was I? Okay. So we've got equations, and we've got these components that are going to be connected: pipes, accumulators, and there's going to be different types of inputs. Okay, that'll be these QMs that come in. I guess that actually may be one difference, and so maybe I'll just make a note here of that. Here, kind of in our electrical analogs, we've got this, and we've got this. Okay. And if you see things like this, when you kind of want to treat this is a constant current symbol, and that would be, if you're doing the electrical analog, that would be the constant mass flow rate in. Constant mass flow rate in. Whereas this one would be a constant pressure somewhere. In both instances, you're going to have something that's driving this process. Either you got a spigot on, you got a valve open, and you got this mass flow rate that's just coming in, okay? Or you've got a someplace where you've got a constant pressure differential, and that's doing there. Is that something for us that I know you're kind of talking. Y'all usually have good things. Was this a comment about this?
No.
Okay. Okay, so I wasn't trying to embarrass you. You know how sometimes teachers will call you out and say, "Hey, well, let's all read the note out loud." It wasn't that. It's just that I know sometimes you have insight that you share with each other. That helps us. If you have some, blurt it out. You're welcome to go on. Oh man, I want to do some examples. Okay. I hope. Oh wow, this is kind of. Well, yeah, I don't know. It's not as messy as I usually do it. Maybe sleep deprivation actually does some good. Um, let's talk quickly about the equations for the thermal that we'll use, and I think it'll be very familiar, as we've handled these things. Okay, now we've got conservation of energy. Energy is a Q again. Okay. In this case, like it really is. Like this is what we use in heat transfer, right? It's the Q is a energy transfer rate. And if we want to use a capital Q or E, yeah, this is where I got all flummoxed the other day, talking about rate versus in a system. Okay. And so to calculate our Qs, there's really only two instances that we're looking at, right? It's the Q that is going in or out of a mass or a reservoir, and then we've got the Q that's crossing at a boundary, okay? And that's very similar to the Q, right? So that would be similar to the mass flow rate coming out of an accumulator or the mass flow rate that's passing through a constricted pipe, for example, okay? So where we've got our resistance here, or we've got some kind of accumulation where the heat is going in or out. Maybe I'll draw kind of heat up or cool down there, just to indicate that this can often go both ways. Interestingly, we kind of handle these the same. Okay, so we've got this energy in a system, this Q. Okay, where this is our the flow rates. More importantly, let's talk about what these Qs look like, and then you'll see kind of where this relates to all of these others and how it works together. And then we can look at a few examples. Okay. Maybe E would be good there. Okay. So for convection, conduction, that's the one. That's one of the symptoms of me not getting sleep is I forget words, like simple words. We could do this in Spanish. That'd be good. Okay, in both cases, the equation for our Q is going to be this 1 over R delta T. This is very much like our Ohm's law. Okay, and so a convenient way then is just going back to the Ohm's law. You can do, develop the circuit. You can solve it all. You can solve it all that way. Okay. So you've got two different things for R. R for convection. I keep getting these mixed up. Is it L over Ka? No, that's for conduction. Is it? And then R for the convection. I'm used to doing the delta T, so HA. I think it's just, is it HA? Is that right? That'll be on the sheet. I believe that's what it is. HA delta T, Ka over L delta T, when we're talking about our heat transfers. Okay, so coming and going, these are going to be our resistances, and these are going to be the equations that we're gonna generate for this. Okay, for the accumulation, so I want to make sure. Oh, we need to talk about what that C is. Um, my mind just drew a blank. Oops. dt um, yeah, I just lost all my thoughts. I'll pull this up. For the thermal, it's this MC Q equals MC delta T. And so I want to put that into this integral form so that we can relate that back to the kind of the electrical system. I can look that up. Yeah, I'm sorry. I just drew a blank. That does bring up though. This talk about the C's that we need to have. Maybe I'll. So when we talk about the C's here, for the thermal, this is the capacitance, or excuse me, for the fluid. Capacitance C is going to be the mass divided by the pressure. Okay. For the electrical, capacitance C is going to be the charge Q over C is going to be the Q over the voltage. Which would make this C to be equal to the temperature over MCP. Huh? Yeah, I don't know. That's crazy. I mean, we gotta have it. Let me look in the thing with the paper and it's bound. Right there. Oh. Guess I could have written that in. Okay. So for these thermal systems, yeah, I think it's got it out. Conservation of energy is going to be our primary equation. There's not usually going to be a combination of conservation of mass and conservation of energy. Okay. And then we're going to have Q's. It's going to be, the Q's is 1 over R delta T. Or it's going to be this MC delta T. Those are going to be our Q's, and we're going to equate them. And talk about capacitance. So let's look at an example. Oh, so I must say that while in our electrical system we do have an inductor, which is this inertial component, there's not inertia. We're not addressing the inertia in fluids, and I'm not sure of any scenario where there's inertia in thermal systems. I mean, unless you're talking about like a phase change, but we're not dealing with that. Okay, and so again, these are all going to be kind of these first order equations that are combined. All right. So let's just kind of talk about some of these examples. Let's start with a fluid. Okay. Okay, and we've just got some. We've got some coming in. There's water coming in. Let's say we've got water going out here and here. Wherever there's coming or going, look for these resistances. Okay, if there's resistances, then that means that's going to help us find the answer. If there's not resistances, then that's just going to be a given or known value, right? I mean, if there's no resistance here, then the water never would get up. If there's no resistance in this pipe, then the water would never ever get above this line. It would just go straight out and as fast as it comes in, okay? So we can consider there's going to be some resistances. In situations like this, we want to look for what is driving this. Is it a constant pressure or is it a constant mass flow rate? Okay. Sometimes it's neither. Okay. That might be useful to when we talk about the electric. I feel like I'm doing more meta problems than actually problems, which is the case. When we talk about the thermal, the fluids, and the electrical, there's really two scenarios. Okay. Okay, number one is a driving potential. And number two is a pre-charged system. Okay. This would be an example here of a driving potential, right? So that would be a driving potential. A pre-charged system would just be something like this. Often, the way I've been doing it in the problems, I'll put valves there or something. I'll put valves there. Won't put anything else. Valves or not. Okay. If you see valves, you can expect this kind of pre-charged system. That is, everything's stationary. I've got a bunch of water in here. I open my valves. What's going to happen? Okay. What's going to happen is this thing's going to drain empty eventually. Okay. For the electrical, a driving potential is going to be anything like that. Okay. A pre-charged system for the electrical will definitely have a capacitor. Okay. And there'll be either a switch. They'll say, okay, we're going to close the switch. What's going to happen? Or it'll be, okay, we're turning on the voltage here at time 0. This talk of time 0 and that sort of. You've seen examples like this of this pre-charged capacitor. Turn it on. Again, usually you're going to have this kind of draining effect. It's going to drain out just like the tank. but you're going to have some behavior while it's draining. I say draining because you'll likely have a resistor in this circuit which will cause that decay. That's the damping term. Resistance here is also in the damping. Okay. For the thermal, it'd be a flame. It'd be some heater element or something of that nature that will give it this. Okay, you've got this input here. Okay. This would be the driving potential. Let's put dP here. Okay. For the pre-charge system, PCS, this is where you've got things of two different temperature that are now coming together. Okay, either I'm taking the lid off, I'm exposing it to the air, or I'm putting my tongue to the frozen pipe, or I drop it in the water to quench it. Okay, that's going to be, so when you think of systems like this, your electrical analog is going to have some input. Okay, either a temperature difference, which would be this. Yeah, so this one, I'll point here, that'd be easy. This would be a temperature difference. This would be a heat input, right? For the fluids, the flow rate would be an input that looks like this, kind of a current. So this is the flow rate. This would be a pressure difference. And then for the electrical, it would be those. Okay. I got a little bit sidetracked. Okay, so in a situation like this, I'll start up here and I'll kind of think about this. I'll say, all right, this is going to be a constant mass flow rate. Okay, so my mass comes in, and then it can either go, let's see, it can either go here, it can go here, or it can go here, which will cause that height to raise. Okay, so there's three different places that this water can go. Would you agree with that? Okay, and so when I'm drawing this, let's say, there's three different places that the water can go. It can be stored here. It can go out here. Or it can go out here. you'll notice in the solutions that I've started to maybe be a little bit more rigorous and say that these gold lines is atmospheric pressure. Okay, so certainly on the outside of this accumulator, meaning on the top side of this accumulator, this is atmospheric pressure out here, and we're saying this flow at some point is going to become atmospheric pressure, like that. Okay, that helps us a little bit when we do our tracking, and we can also see, okay, now our pressures, our pressures are the thing that kind of behaves like our voltages, and the mass flow rates are like the current. Okay, so we're going to have some Q here. And then we've got our pressures. You know what? I may need to add something here. So this, I'll call this PA. Notice PA is the same, right? So this PA across here, this is actually going to be lower. Do I need another resistor in here? We'll go and look at it like this. Okay. What we've got is pressures. Yeah, I think we'll need to insert a capacitor in here. No, it'll be another resistor. No, 946. It's after time. It's after time. I'm not gonna keep you. You'll see. Yeah, my intent was to create a circuit, and then we'll use all of our circuit stuff to solve this. There's plenty with Chapter 5 homeworks, with the Chapter 6 homeworks. There's going to be plenty of examples like this of worked out. I hope you'll take the opportunity to kind of step back, just flip through the book, look at problems, and just think through and try to make heads or tails of this. All right. Thank you very much. Sorry for the minute over. Whew.